good way to understand the vector outputs and to better visualize what they do is to use them as texture coordinates for an image. Let me make some room here. So I'll press Shift A, texture, image texture. I'll choose a person's face, preview. Okay, this is the original unaltered image. And if I use my stepped vector output, I get a pixelated image effect. And you'll see that each tile in this case seems to have a border, a slightly different colored border around each tile in an Eevee preview or render at least. In cycles, that artifact is not there. So to remove that effect in Eevee, simply change the texture interpolation of the texture node from linear to closest. And you'll see the borders are gone. So now, let me add a converter vector math node. We'll leave it set to add, and now we'll add the standard vector output to the stepped vector output, and we have managed to return to our original unaltered image. And you might be wondering why that's useful. Well, the point is that now we have these two vector inputs which are combining and both contributing to the final output, so I can interact with both of these vectors in different ways to produce different effects. Let's begin with a vector rotate node. I'll drop it on the standard vector output. And in this case, we're using a UV map, and our standard vector output has useful X and Y components, so we can rotate around the Z axis. And now if I click and drag on my angle input, you'll see that we can rotate each individual tile of the image. All the tiles are rotating around their bottom left corner, and that's because the center point is set to 0, 0. If I want the tiles to rotate around their center point, all I have to do is to enter the width and height values here, multiplied by 0.5 or divided by 2. The values are currently 0.1, which divided by 2 is 0.05, and they're both the same, so I want to enter 0.05 into both of these input fields. I'll click and drag across both of them, release, and now type in 0.05 and press enter to enter that value into both of the fields. And now I can click and drag on my angle input, and the tiles are now rotating around their center point, exactly like I wanted. The tiles, however, are all rotating in the same way and by the same amount, i.e. the angle that I input here, which is certainly useful and maybe what you want, but it might be more interesting to add some random components to these transformations, and we can do that with our random color. So let's grab a converter separate RGB node to break apart the random color. So now we have 3 sets of random values to use, and we can plug a random value, for example this blue value, straight into the angle input of our vector rotate node, preview the image output, and you'll see that while we do seem to have random rotation, there's something going on. None of the tiles seem to rotate past 45 degrees or thereabouts, and they all certainly rotate in the same direction. Let me add a multiply node, which I can use to control this angle input here. I can now lower this result, or lower this input field to remove the random rotation. A full random rotation of 1, you'll see it doesn't in fact rotate past 45 degrees. That is explainable by the difference between radians and degrees and the foibles of the vector rotate node, which are these. If you interact with the angle input socket directly by either clicking or dragging on it to change the angle, or by entering with your keyboard, entering a numerical value, the node interprets this angle input to be degrees. So if I enter 0, this is the unaltered image, 45 rotates each pixel, or each tile in this case, by 45 degrees. 90 degrees is a quarter turn, 180 degrees is a half turn, and that makes sense. The color outputs, however, the 3 channels of the color outputs arrive in a 0 to 1 range. So theoretically, if I connect one of these channels to my angle input, I should be getting random rotation between 0 degrees and 1 degree. That's clearly not what's happening here, because if I enter 1 degree numerically, you can barely see the change. If I zoom way into the eye, for example, reset this back to 0, you can see the tiniest rotation. So there is more to this than meets the eye, pardon the pun. So there is more to this than might be immediately obvious. The problem is that if instead the angle input is connected to any other node of any type, the vector rotate interprets this input as radians, so a value of 1 will barely give me an eighth of a rotation, because a quarter of a rotation, i.e. 90 degrees in radians, is about 1.571. 180 degrees is 3.14, which you may recognize as pi, and so a full rotation in radians would require a value of pi times 2. So I can multiply a value, a simple 0 to 1 value, by 3.14 multiplied by 2. As a matter of fact, did you know, for easy access to the irrational number pi in Blender, you can simply type into an input field the letters pi or pi, press enter, and Blender will enter the numerical value for you of 3.14159. It's truncated, but the value is much more precise than simply typing 3.14. The beauty of this method is that the word pi can be treated as a number. For example, you can type in pi, then multiply 2, and you get the numerical value of pi multiplied by 2. It's really very useful for cases like this. Plugging this value directly into my angle input will give me a full 360 degrees of a random rotation, with the small issue that it's not an issue, the small detail that all the tiles are rotating in the same direction. Again, let me add a multiply node so I can control the influence of this rotation. A full rotation of 360 degrees looks like that. I can back it off to 0, no rotation. You'll see all the tiles are rotating clockwise as I reintroduce the rotation. To fix that, we can remove this multiply node. We no longer need it. We're going to add a converter map range node. We'll plug the blue component of our random color into the value input of the map range node, and we'll plug the result directly into the angle. Now we can come down to 2 max and type in again pi times 2 for the same result we had before. But because we want to rotate from minus 180 degrees to 180 degrees, which is tantamount to rotating between minus pi and positive pi. And as simple as that, we have random rotation moving both anti-clockwise and clockwise, which again I can illustrate with a control multiply node. Let me roll off the rotation. I can even go into minus numbers to invert the rotation, or go past 1 to exceed the 360 or 180 degree rotation in this case. You will notice, however, that while clicking and dragging on a math input node, it's true that you can hold shift for extra precision. In fact, it's precise to the nearest hundredth, but in certain cases that may not be precise enough. And there is a better type of slider available in Blender, and we're going to combine the qualities of that slider with the functions of a multiply node and wrap it all up in a new node group, which will become a very useful utility node called a fader. Select the multiply node and press Ctrl and G to wrap it up in a node group. Now let's press N to open the side panel, click on the group input node, open the node tab, and we can delete the second input value because we do not need it. Now to obtain this high precision slider, as I'll call it, it is now available in Blender in a mix RGB node. This slider here is much more precise. Even without holding shift, you can immediately see that I'm getting precision to the nearest thousandth, and that's not holding shift. I can then hold shift and drag with incredible precision. Now there's no output, so you can't actually see what I'm doing, so let's move on. We're going to connect this FAC input node to our group input node here, and now we can simply delete the mix RGB node because we do not need it. We can connect the FAC from our group input into the bottom of the multiply node and directly through to the group output node. We'll leave it named as FAC. Now we can press tab to leave the node group, and here is our fader group, currently called node group 1, so we'll give it its name, fader, and click the shield to keep it forever. Now you can see that I can introduce and remove the rotation effect with my super precise slider. I can zoom in real close, and you'll see just how much precision I have when introducing this rotation effect. This is one use case for the fader node. Another is to use it as a value input node, as a substitute for the built-in value input node here. And the reason you might choose the fader over the built-in value input node is precision. If I click and drag on the value input node, you'll see I get precision to the nearest tenth. If I click and drag on the fader node, you'll see I get precision to at least the nearest thousandth as far as I can see. But in actual fact, if I click on this value input node to expose the whole value, you'll see that it is actually precise to an indeterminate degree, because Blender will always truncate values to 6 decimal points. So this value could be even more precise than is represented here, and the precision goes even further if you hold Shift while clicking and dragging. You'll see that the slider moves much more slowly, offering you much more precision and control. The value input node, even if I hold Shift while clicking and dragging, is only precise to the nearest hundredth. The factor input of the fader node, which passes straight through the node and comes out here as an unaltered value, is limited to a 0 to 1 range. This can be overcome if you need to by clicking on the value field and inputting a number greater than 1, for example 2. Now I can slide back and forth between 0 and 2, but there is a small detail. As long as I stay above 1, when I release the value, I'll be able to return to 2 and down as far as 0. However, if I release the value below 1, you'll see that it reverts to a 0 to 1 range. Another way to alter the output of the fader node if a 0 to 1 range is not desirable is to use the value output. Remember that the fader node essentially multiplies its value input by this factor. So if I set the value input to 1, the value output will give me a 0 to 1 range, unaltered. If I set this value, however, to 3.2 or something arbitrary like that, this factor now slides between 0 and 3.2, exactly like a multiply node would do, but with super precision. And that's the fader node and some of its use cases. Now let me just get rid of this one and reconnect my map range node for random rotation. And let's have a look at some random translation. Actually, no. Let me plug the fader node back in there. And we'll keep that as a rotation control node, or control switch, I suppose. Next, we'll take a converter vector math node and drop it onto the stepped output. I can now translate my tiles left to right and up and down, but they're all being translated by the same amount, and so the movement is uniform and not very interesting. I can use the red and green outputs, combine them into a vector, and add that vector to the stepped output to obtain random translation per tile. So let's do that. We'll grab a combine XYZ node. We'll plug red into X and green into Y. The combine node goes into the bottom of the vector math node, and there you have it. We got random translation for each tile. The translation is extreme to the point where it's very difficult to understand what the actual original image looks like. Let me come to my image texture node here and change the repeat mode to clip. Now I will see black beyond the extents of the image itself, beyond the boundaries of the image. Let me drop in a fader node onto my red and green values here. I'll now select both my fader nodes and hold Alt and click and drag on one of the factors to alter them both at the same time. You'll notice that the translation happens in the same direction more or less for all the tiles. All of the tiles move to the left and downwards. None go up or to the right. And that is because, again, these color values are in a 0 to 1 range. If we want the tiles to translate both left and right and up and down, we must remap them from a 0 to 1 range to a -1 to 1 range. which we could do again with the map range node, but really the map range is entirely too much for these purposes. This can be done in a much simpler way. All we have to do is drop in a few math nodes. We'll begin with a multiply, set to multiply by 2. We'll duplicate that one and drop it to the right, set it to subtract and subtract 1. This has already changed this 0 to 1 value into a -1 to 1 value. Let me do the same for the green channel or the Y component, whichever way you want to look at it. There you go. The final step is to add some control nodes, some simple multiply nodes, which we'll use as control nodes. We'll drop that there, duplicate it, and drop one there for the Y. And now I'll duplicate my fader node. I only need the factor in this case from 0 to 1. So I'll plug the fact directly into the bottom of both of my multiply nodes. And now I can introduce random translation left, right, up, and down, and I have control over just how far it actually goes. I could even push this further by connecting to the value output of my fader node instead, and control how extreme the translation is by changing this value here. I could set that higher to 2.8, for example. And now I get much more translation to the point where nearly all of the pixels disappear. Let's actually increase this value until all the pixels are gone. And now we can bring them all back in and all back out with one simple value sweep. Pretty cool. These effects really come into their own when used in combination with motion graphics, with a video or an image sequence in this case, because we can't use video files in the shader node editor. If you don't have an image sequence ready to use, Blender can convert a video file into a sequence of images for you. Let's start by opening a new instance of Blender. We'll go to File, New, then Video Editing. No need to save this. Now open a browser window where you keep the video file you want to convert and drag it into the video sequence editor. Let's go back to Blender. Press Page Up on your keyboard to go to the end of the strip. Now press the left cursor key to go back by 1 frame. Now hold Ctrl and press End on your keyboard to set the end of the blend file to the end of the video strip. Now let's go to the Rendering tab here. And now in the Properties panel, we'll go to the Output Properties tab. And under Output, we'll select the path where we want to save the images of our image sequence. Incidentally, ping will be fine, but I'm going to set this color mode to RGB because I don't need alpha. Now I'll browse to where I want to save my image sequence here, for example, and click on Accept. Now all I have to do is to render the animation, which I can do by pressing Ctrl and F12, or come to the Render menu here and click on Render Animation. Let Blender do its thing for a short time, and when it's done, you can hold Alt and click on the folder icon beside the image sequence path here, and it will open a browser window with all of the images saved therein. All the frames of your video now converted to individual images to be re-imported into Blender and used in our UV Grid shader. So let me choose an image sequence, turn on auto refresh and play to cache the images. Give Blender a little time to load all the images available. As a matter of fact, there are 197 frames available for this animation, not 100. Blender will cache all the images and playback will become smoother. There we go. And now we can start to introduce random rotation as we did before for the faceted, mosaic, kaleidoscope type effects, and the random translation to move the pixels around just like before. Bring them all back in. Now you'll see there's a small scaling issue because my video file is 1920 by 1080 resolution and my available geometry is a square. So I can fix that with some vector math nodes immediately before the texture node here. So the last transformation that happens to the texture coordinates before they enter the image texture node. The first vector math node gets set to multiply, and we'll set the x and the y values to 1 for an unaltered image. The second vector math node will set to subtract, and you'll see we can now use the values of the subtract node to translate our image, and the values of the multiply node to scale the image. Let me reset all of these to default. Now I need to alter the X scale of my image to compensate for the distortion introduced by fitting a rectangular image to a square piece of geometry. And I happen to know that my image is 1920 by 1080, so to fix the X scaling issue, all I have to do is divide the height of the video file by the width, which is 1080 divided by 1920. Enter, and the image is now correctly scaled. I can simply slide it into place with my translate controls here, and we are ready to go. Random rotation, random translation, and everything is looking very eclectic. I think you'll agree. However, one nice little effect that I managed to come up with by accident, you may have seen it on Twitter, was this. I'm going to remove the standard vector addition completely by pressing M on the keyboard to mute this node, and I get my pixelated view back. And now I can set the height of the individual tiles to something much smaller than the width. Let's set it to 1/10 of the width, 0.01. Play the video, and you get this very nice soft blending effect. I say soft, it's soft vertically and very harsh horizontally. It's a nice effect, I enjoy it a lot. Let's try a different video and see how we do. The first playthrough will be a little slower as Blender caches the images. Let's see what it looks like if we invert the relationship between the sizes. We'll make the width 0.01 and the height 0.1. Interesting. If we bring the standard vector back in, we can introduce rotation in these very, very narrow tiles, which looks interesting. Let's invert the relationship again. And some random translation to destroy the image completely and have no idea what it's actually supposed to be. Very nice. Images, image sequences, whatever you prefer, it's all good. UV Grid can do it all. And that's it for this video and our first experiments with our UV Grid node. In the next video, we'll take a closer look at the stepped output and how we can use it to create pixelated images, and also the normalized output, which we will use to create some procedural bump maps combined with pixelated images to create an LED type display. I hope you enjoyed this video and found it useful, and I look forward to seeing you in the next one. Take it easy.